Okay, we're going to talk a little bit more about logarithms, the graphs of y equals x to the p and y equals the log of x to the p. This looks a lot like what we did here, but the result is going to be somewhat different. You recall that if you take the graph of b to the x, you get an exponential graph, either a decreasing exponential if b is less than 1, an increasing exponential if x is greater than 1. So here are three graphs for b equals 1/2, 2, and 8. And here are the graphs of log of b to the x for those same values. So the decreasing purple graph corresponds to decreasing purple graph here. Decreasing orange and blue graphs correspond to the increasing, did I say increasing? Orange and blue graphs correspond to the increasing orange and blue graphs here. These graphs become linear. If you take the logarithm of an exponential function, you get a linear function. And algebraically, it's pretty clear why that's the case. Excuse me. Okay. Now, we want to, again, come back to the idea of the graph of the log of a power function, a function of the form x to the p. Okay. So just for example, let's take the graph of y equals x squared. So here is a somewhat skewed right curve, okay, but represents the graph of y equals x squared. We want to look at the graph of y equals log of x squared, so log of x squared. Now I want to just select three x values, and I'll explain why I select these three in a minute, and don't select the others. And one explanation is if x equals 0, x squared is 0, and the log of 0 is undefined. You recall the graph of the logarithm is asymptotic to the negative y-axis on the positive side. Okay, so log of x squared. Okay, if x is 1/2, x squared is 1/4. The log of x squared is negative log of 4 which I'm going to write as negative 2 times the log of 2. And this should be clear. Well, I'll say it, I don't want to write it out. But 4 is 2 squared. The log of 2 squared is 2 times the log of 2, and you got the negative sign. Okay? And the reason the log is 1/4 is the log of 1/4 is the log of 1 minus the log of 4, and that's 0 minus the log of 4. And we used those in the preceding video, and that would have been reinforced by the problems that went with that video. Okay, so we have this. Now the log of x squared, if x is 1, x squared is 2. No, it isn't. If x is 1, x squared is 1. And we get log of 1 equals 0, because again, b to the 0 is always 1, and the log is the inverse of the exponential function. And then 2, 4, okay, we get, when x is 2, x squared is 4, log of 4 is 2 log of 2. So we have negative 2 log of 2, 0, 2 log of 2. Equal increments here. So you would think this graph would be linear until you actually make it and think about what you didn't think of. So let's make the graph. And we only need positive values of x. So remember, x equals 1/2 gave us negative 2 log of 2. Okay? So, in other words, When x is 1/2, x squared is 1/4, so the log of x squared is -2 log of 2. We're doing log of x squared now. So let's say here's 1, here's 2. And we're going to draw a scale here. We'll have negative, actually let me put negative log of 2 here. -2 log of 2 here. Log of 2 here. 2 log of 2 here. So when x is 1/2, log of x squared is -2 log 2. That's going to be down here. When x is 1, we get 0. When x is 2, we get 2 log of 2. So these values on the y-axis are equally spaced, but the values on the x-axis aren't. First value is at 1/2, second value is at 1, and then third value is at 2. Shorter interval between here and here than there is between here and here, and that's what makes this graph curve in such a way that it's concave down. Okay, what other graph do we know that curves when it's concave down? Well, the log graph curves when it's curves concave down. It's also asymptotic to the negative y-axis, and it turns out this is just a multiple of our basic log graph. Okay, so let's see why that is. Y equals the log of x squared, which of course is 2 times the log of x. Okay? So this is just the base 10 log vertically stretched by a factor of 2. And that's what we have here. And you know, from what we've seen a couple of assignments earlier in this thread, that any log graph is a constant multiple, a constant vertical stretch, a constant relabeling of the y-axis of another log function. So there it is. Also, we could say since the log of x is the base 10 log, I used to know how to write and talk at the same time. Didn't leave myself room. I'd rather not pretty bad, but anyhow, so I'm going to write it out again. Apologies for wasting a little bit of your time, but think I'm going to do this. And what I did wrong the first time I wrote it is 2 times the log of 10 over log of 2 times the log base 2 of x. And that's because the log of 2, log base 2 is log of 2 divided by log of 10 times the log base 2. Okay, just a rule that we've had for quite a while now. I think I said that right. Okay. Point is, this is just a vertical stretch. Of the log base 2 graph. And for homework, you work out some of the algebraic details. They're simple. People did quite well on this stuff at the midterm. So you should have no trouble. You might have to refresh yourself a little. Okay? Now, in general, the log of y equals log of x to the p just p log of x. So if you have a graph of the log of x function, and p is 2, you're just going to vertically stretch this function by factor 2. Every point move twice as far from the x-axis. So here is y equals 2 log of x. If it was x to the third, so we'd be doing the log of the cubic function. We'd have a point probably down about here, points up here. Everything would meet, and x equals 1. There's a graph of y equals, let's see. This would be y equals 3 log of x equals log of x cubed. So we have y equals log of x, y equals log of x squared, y equals log of x cubed. Just vertically stretching. The more we stretch, the higher the power of x, for which we're graphing log of x to that power, the graph of log of x to the p. And of course we could have a negative vertical stretch. Put that in the wrong place. This could be y equals -1 times log of x. Of course, that's just negative log of x, but I want to be explicit about the 1, equals log of x to the -1, which is the log of 1 over x. Okay, now all this is wonderful. It's good. It's fairly simple if you understand the rules for logarithms, but it's not that simple because there are a couple of steps. It's not overly complicated. It's within range of something that we could expect a pre-calculus student to ponder and understand. But what good is it? Well, you notice that the log of an exponential function always gives you a straight line. The log of a power function, and power functions are all over the place, always gives you a line that's concave downward, has the same shape as logarithmic graph, as a logarithmic graph, yeah. Okay? So the log of a power function is just a vertically stretched logarithmic graph. And we want to see how that works with different ways in which things can grow, and in particular with different ways in which a virus can spread, or an infection, or for that matter, a mutation, and good mutation, bad mutation, good mutations have apparently led to us. I think that was good. So, you know, this is very relevant, even on a cosmic scale. Okay, so we'll talk about it a little more.